Thank you for introduction. And I'd like to thank the organizers for invitation. It's a great honor to give a talk in this conference in memory of Fred Cohen, who was my advisor. So, let me begin with some memories with Fred. Before I became a student of Fred, I met Fred in Japan. There was a big conference for Toda's 60th birthday in Kinosaki, and I was a student at the Kyoto University, and I was interested in iterated loop spaces and did some calculations with Araki Kudo Dirac operations. And during the conference, Mimura introduced me to Fred, and I showed him some calculations I did, and he sat down next to me and patiently listened to me. And my English was not very good, and he wrote down everything what he said onto his notepad. He was really kind, and I was very impressed. And after the conference, Akira Kono suggested me to go to Kentucky to study with him. I thought it's a good idea, and I tried to apply to Kentucky. And it turned out that Fred was about to move to Rochester. So, there are some confusions, but somehow I could get to Rochester, and I became a student of Fred in the next year. I was lucky, I think. And when I arrived at Rochester, I went to see Fred. And the first thing Fred said to me was, "Did you find anything to eat?" What? I didn't understand. I said, "Oh, I can eat anything. I can eat McDonald's." Said, "Oh no, Dai." He was very upset. It seemed that he was really impressed by the food he had in Kinosaki. So he thought I shouldn't eat American junk food. And then next week I went to Fred's office, and he said, "Did you find anything to eat?" So he just didn't believe me. And after a couple of a month or something, so I walked around in downtown Rochester, and I found an Indian grocery store, and I liked spicy food, and I got some spice and cooked by myself, and I told it to Fred, and Fred was very happy about that, and he started talking about hot foods, like hottest chili in the world, and buffalo chicken wings, and he also talked about garlic chocolate and so on, and so when we meet in his office, he also talked about what he did when he was young. He talked about hitchhiking to Afghanistan, canoeing down to canoeing the Mackenzie River to the Arctic, and of course rock climbing. It was really fun. I liked Fred very much. And of course, I got many ideas from Fred. The one of the most important event was trip to Baltimore. He gave a ride to an AMS meeting in the Johns Hopkins University. That's because I was interested in Moravec's theory of iterated loop spaces. And at the time, Steve Wilson had a student who was also a Japanese working on Moravec's theory of infinite loop spaces. So Fred wanted me to talk with him. But our discussion was not very successful. But on the way back from Baltimore to Rochester, Fred explained me an idea of filtering configuration spaces. So if you have a configuration space of, say, j points in Rn, so this is the first coordinate, and the rest. And we have some points. Then some of the points lined up on the vertical hyperplanes. So he said that if you filter the configuration space by the number of hyperplanes, vertical hyperplanes, then we will get the Allenberg-Moore spectral sequence. I was really amazed by the idea. But if you, but these are points in the configuration space of Rn-1. So it looks like a Koba construction. So the configuration space of Rn-1 just lined up and looks like a Koba construction. So I understood the idea, and after I came back from Baltimore, I tried to work out the filtration, but I found that it's not easy to work with configuration spaces, because if we use configuration spaces, it's not easy to show that the successive inclusion of the filtration is co-fibration. So in order to get the spectral sequence, we need a long exact sequence in homology. So we need co-fibration. So I decided to translate everything into little cubes, and then I succeeded in constructing a spectral sequence, and it was my thesis. And another important event, I was a conference for Fred's 60th birthday. Around, I think it was 2003, Doug Ravenel emailed us, former student of Fred, Ron, Jay, and Miguel, and me, saying that Fred is going to be 60. Are you planning a conference for him? We had no idea. But we thought we should have a conference. But none of us had enough grant, and we didn't know where to have a conference. But at the time, I noticed that Toshitake Kono at the University of Tokyo had wrote a joint paper with Fred. And I knew that usually professors at the University of Tokyo have big grants. And the University of Tokyo also has a very nice conference room, big conference room. But I didn't know Toshitake at all. I've never seen him, but I just tried. And I asked him to host a conference for Fred. It turns out that Toshitake liked Fred very much, personally and mathematically, and he was really happy to have a conference there. And also he's very smart that he did almost everything for the conference. Actually, he hired secretaries for the conference, and the secretary did a lot. And I thought it was a good way to run the conference if we have big money. Anyway, many people came to the conference. I was amazed. About 200 people came to the conference from all over the world. So I was really amazed that so many people came to Tokyo to celebrate Fred's birthday. It was really amazing. And the last thing I want to talk about Fred's idea is the center of mass arrangement. when I received an invitation to this conference, I thought this is a topic I should talk, because this idea was not is not very popular, but I think this is a very good, very interesting idea. The idea is to use so the braid arrangement is defined by these equations. But if you have subsets of this set, and we can define a hyperplane. By this equation, and some collection of these hyperplanes form a center of mass arrangement. This hyperplane arrangement is very interesting, that in the sense that we can use this hyperplane arrangement to construct the secondary EHP sequence, which was proposed by Brighton Gray. So the idea is to split the in order to split the periodic part. The best possible we can do is the 2p times suspension, but if we use Fred said that if we use these hyperplanes, complements of these hyperplanes, we can and if we localize that an odd prime, then we can reduce the suspension to the twice. Ah, yes. And if we can do that, then we have very good chance of constructing a secondary EHP sequence, which is an EHP sequence for Moore spectrum, mod P Moore spectrum. And I did some calculations but the calculation was very complicated, and I don't think it's a good idea to talk about this in this conference. So I decided to talk about something else, which is about homological algebra. So recently I noticed there are two generalizations of chain complexes. One of them is due to Kopanov. So in his approach, we regard the chain complex as the module over the exterior algebra. So he proposed to replace the exterior algebra by a finite dimensional Hopf algebra. Then since H is a Hopf algebra, the category of H modules has a monoidal structure, which is a generalization of the monoidal structure of the category of chain complexes. The monoid objects in the category of chain complexes is a differential graded algebra. So the corresponding object in the Hopf project case is called H module algebra. And we can also define, derive the category. We can also define chain homotopy, analogs of chain homotopies and homology and so on. So this is very nice. But so in Kovanov's approach, gradings are not. We can put gradings, but we don't need gradings at all. And n complexes. N complexes so it's an analog of chain complex as a generalization. The composition of consecutive n differential is 0. Okay. So, right. So in Kovanov's approach, it's not easy to handle chain and n complexes. And there's another one due to Holman and Jorgensen. And they regard a chain complex as a functor from this category, so that so we have a relation that this is 0. This is also a very natural interpretation of chain complex. So from this viewpoint, we can replace this category by a functor from a category, from a linear category. But of course, we need to put some assumptions on Q. But in the approach, we cannot have a monoidal structure in general. But good thing is that we can use objects of this category as gradings. And also we can put n complexes in this context very naturally. So this is a plan of my talk here. So I first review Homological homological algebra, and then in order to what I want to do is to define multiplicative structures in the context of Homological and Jorgensen. And what I want to say is that we should use the notion of Duoidal category to do that. And then I say something about monoidal model structures. And if I have time, I want to say ask some questions. So let me fix some notation for linear categories. So I want to regard linear categories as a monoid object in the category of quivers. So for simplicity, I just want to fix the field K, and a K-linear quiver is just a bigraded object in the category of K modules. But since this is a bigraded object, we can regard a quiver as a bicomodule over the co-algebra generated by the set gamma. Then by using this commodule structure, we can use the cotensor product of quivers. And then we get a monoidal structure, and we have a monoidal category of quivers. And a monoid object in this monoidal category, by definition, it's a k-linear category. And I learned this viewpoint from a paper by Day and Street. And in order to do an analog of homological algebra, we need to put some conditions on the k-linear category. So there are many conditions that Holm and Jorgensen used. But these two conditions, the first two conditions are some finiteness conditions, and the 4 and 5 are some kind of nilpotency conditions. But I think the most important one is the third one, the middle one. And so the condition is the existence of a cell functor. If we switch source and target, we can use the functor S to switch source and target and take the linear dual to get the original morphism space. Okay, so this is so this is a category for chain complexes. So the category of chain complexes is almost by definition is equivalent to the category of functors from this category to the category of K modules. And this category is the category that satisfies the last 5 conditions is called Holm-Jorgensen category. And this is a Holm-Jorgensen category because the cell functor is defined by shifting by degree 1. So we can also have the DGN is a category for n complexes. So this is also an Holm-Jorgensen category, and its cell functor is defined by shifting by degree n-1. And the next example is key example which connects two approaches to homological algebra. So suppose H is a connected Poincare algebra, which means that it has an augmentation of degree -1, and such that the pairing, the multiplication in H and composed with epsilon is non-degenerate. And we also assume that each HI is finite dimensional. Then we can define a category LH. So the set of objects is non-negative integers. And the modulo of morphisms from I to J is H sub I J minus I if J is greater than or equal to I, and 0 otherwise. And the composition of morphisms is given by the multiplication in H. Then this is an Holm-Jorgensen category because the cell functor is defined by a shift of degree n. But because of this the assumption, so this map is non-degenerate, and by taking the adjoint, we obtain an isomorphism that we need for a cell functor. So the existence of cell and an important example of Poincare algebra is finite dimensional Hopf algebra. So this example has this example connects these two approaches. And we see that the existence of cell functor is very closely related to the fact that H is a Hopf algebra. Okay. The next thing is to define a monoidal structure on the category of modules. So for K-linear category, left module over Q is just a covariant functor from Q to the category of K modules. But we can also regard it as a gamma graded object with an action of a Q. So if you have a gamma graded module, so we can regard it as a gamma comodule. And our category Q is also a gamma bicomodule. So we can take a cotensor product. And the structure of functor defines a map from Q cotensor with M to M, which is associative and unitary. So it looks like a usual definition of the module. And in the case of a Hopf algebra, the monoidal structure on the category of H modules is defined by the following composition. We first take the co-multiplication of H and then switch H and M, then apply module structures of M and N. Which means that in order to define a monoidal structure, we need a co-multiplication on Q. And we also need this kind of switching operator. Yes, we need a comonoid structure on a Q and switching operator. That's where the notion of duoidal category comes in. It was introduced by Aguirre and Mahajan in their book, published in 2010. But they called it two monoidal category. But nowadays, it is called a duoidal category. So I want to call it a duoidal category. And here is the definition. It's a category which has two monoidal structures. And we also have a natural transformation, which switches middle two terms, middle two factors, also to monoidal structures. And we also require three morphisms on those unit objects. So since this zera is a kind of switching operation, we need to require that it makes a hexagonal diagram commutative. It looks like a braiding in a braided monoidal category. In order to define a duoidal category of quivers, we need to put some more assumptions on our vertex set. So we assume that the gamma is a commutative monoid, which is a submonoid over an abelian group. And let Q plus gamma be the subgroup, full subcategory of the category of quivers consisting of objects such that the module of morphisms from X to Y is 0 if Y minus X does not belong to gamma. Then we define a monoidal structure by the usual monoidal structure for graded objects, graded modules. And if we have a symmetric switching, symmetric bilinear map, which means that it converts an addition in gamma to a multiplication in k, and they are symmetric. It is symmetric. Then we define an associated twisting operator sigma tilde by switching to factors a and b, and then multiply sigma of y minus x and w minus z. And by using the sigma tilde and the symmetric monoidal structure of k modules, we can define a switching, we can define a natural transformation that we need for duoidal category. And once we have a duoidal category, we can define a bimonoid object, because we can define a bimonoid object in a symmetric monoidal category. But here we use two different monoidal structures. So a bimonoid object in a duoidal category is a quintuple. So it is a monoid object with respect to the first monoidal structure, and it is a comonoid with respect to the second monoidal structure. And and the rest is the the next requirement is that the multiplication mu is a homomorphism with mu is a morphism of comonoid, and delta is a morphism of monoid. So a bimonoid object in our duoidal category of quivers is called a comonoidal category. So I want to call it a comonoidal category. Then so we have an analog of Hopf algebra or bialgebra in this context. Then we can try to define a monoidal structure on the category of modules of a bimonoid object. Actually, Aguilar and Mahajan developed the theory of modules of a bimonoid object in a duoidal category. But in our case, our Q is bigraded and M is singly graded. They live in different categories. They live in different categories. So we have to modify what Aguilar and Mahajan did in their book. So what we need is an action of a duoidal category on a monoidal category. Then we can define an action of a bimonoid object in this duoidal category on an object in this monoidal category. So this is what we need. And we can show that in this case, the category of modules of a bimonoid object has a canonical monoidal structure. So with this setup, I want to define model structures. Since so we are working in abelian categories, we want to use the Hove's theory of abelian model categories. So Hove proved that there is a close relationship between abelian monoidal categories and co-torsion pairs. So with I first want to record the notion of quotation pairs. So we first define orthogonality by using the vanishing of x1. Then we can define also orthogonality with, from left and right. And a quotation pair in an abelian category is a pair of classes of objects such that P is left perpendicular to I and I is right perpendicular to P. So a typical example is a pair of the whole category and the class of injective objects and the class of projective objects and whole category. Then Hove showed that if we have a triple of subcategories or classes of objects, such that the middle one is a sixth subcategory, and the intersect, so the left one and the intersection of the two is a quotation pair, and the intersection of Kof and Trib and Fib is a quotation pair. If these three conditions are satisfied, we can define an abelian model structure. Such that the Kof is the class of cofibrant objects, and Trib is the class of trivial objects, and Fib is the class of fibrant objects, and vice versa. So in order to define an abelian model structure, what we need to do is to define a triple of subcategories satisfying these conditions. And such a triple is called a Hove triple. So in the case of homological algebra, actually Kubanov didn't work in worked out model structures. So I tried to construct a model structure. So H is a finite dimensional Hopf algebra over a field, and the monoid object in the category of H modules is called an H module algebra. So so this is an analog of a differential graded algebra. So an analog of a differential graded module over a differential graded algebra is it's called an H equivariant A module. And if we have two H equivariant A modules, we can define a notion of H equivariant A homomorphisms from M to N, which is A module homomorphism and H module homomorphism. So the category of H equivariant A modules and H equivariant morphisms is denoted by this symbol. So this is an analog of the category of modules, differential graded modules over differential graded algebra. So in order to define a trivial object, I want to use homology. So in the case of homological algebra, here's the definition of homology. The set of cycles is just a set of invariants. And the set of boundaries is just the image of the multiplication by lambda. Here, lambda is an element of H called an integral, which is an element satisfying this condition. If you multiply any element of the Hopf algebra to lambda, you just get the augmentation of H. Then the quotient is an analog of homology. So in the case of the graded module over the exterior algebra, we get the usual homology or cohomology. And we can also define an analog of chain homotopy. So two morphisms are chain homotopic if and only if it factors through M tensor H. But here we use the integral. So here is the multiplication by lambda. Then by modeling up this homotopy relation, we get a triangulated category. So this is a derived category in the context of homological algebra. And since it is a triangulated category, we should have a suspension factor. And it's given by tensoring with H modeled by the ideal generated by lambda. So this is an analog of a circle. And here H is an analog of an interval. And tensor product is like a smash product in topology. Okay. So Kovanov wanted to study this triangulated category, but I want to construct a model structure for this triangulated category. But in order to construct a triangulated in order to construct a Hovet triple, what we need is this. If we have 6 subcategory, and if it satisfies these 2 conditions, then this triple is a Hovet triple. So all we have to do is to define 6 subcategory of trivial objects and verify these 2 conditions. Okay. So as you imagine, we define trivial objects by vanishing of homology. But in the case of homological algebra, we don't have gradings. We don't have a shift of degrees in homology. So I want to assume that the homology of arbitrary suspension of M is 0. So the first subcategory of an acyclic object is denoted by triv AH. And we can show that this category satisfies these 2 conditions and defines an abelian model structure here. And what about the case of Holm and Jorgensen? Actually, they did very similar construction, but they considered the category of functors from their categories Q to the category of A modules, where A is just an associative algebra. In the case of differential graded algebras or homological algebra, we have an action of Q on A, and everything must be equivariant with respect to the action. But here, in their case, there is no action at all. But anyways, they defined cohomology and homology groups. And it's interesting that it's bi-graded. One of the gradings is given by the homological degree, and the other one is given by the vertex. So it's bi-graded. And that their category of trivial objects is defined by the vanishing of reduced cohomology. Then they showed that this category satisfies the previous 2 conditions, and we obtain a model structure in the category of QA modules. Now, in order to introduce an action of Q in this context, so I first want to introduce the notion of H module algebra for a homological category. So in this case, we work in the category of quivers, and H is a K-linear category equipped with a coproduct. And those monoid, in the case of usual chain complex, if we use the usual sign convention, we get a differential graded algebra. And in the case of n complexes, in the case of DGN, we have Kaplanov constructed a monoidal structure on the category of n complexes if we have an nth root of unity in K by using this sign. And the monoid objects in this monoidal category is usually called a Q differential graded algebra. And as in the case of homological algebra, we can define a category of H equivariant A modules. And I want to define, but for the trivial objects, I want to define by using homogeneous and cohomology. Then what I want to do is to show that this category satisfies the above two conditions, the previous two conditions, so that we get a Hove triple, but I haven't done yet. So here's my guess that so we get a monoidal structure with we get a model structure. Also, what I want to do is to analyze this category, which is perpendicular to the trivial objects. In the case of homological algebra, this is a category of semi-projective objects. So we need a kind of analogous notion of semi-projective objects in this context. So, and this is all I know now. And maybe let me finish this talk by a couple of questions. And so far we have three. I showed three kinds of examples of comonoidal categories. So DG defines the chain complex. DGN defines n complex. DGN defines n complexes, and LH for a finite dimensional connected Hopf algebra defines a category of H modules. So, and I want to, there should be more. And I want to know more examples. So in the case of differential graded algebras, we have many objectification called the differential graded category. And homological algebra of differential graded category has been studied by many people. And it might be interesting to make everything, to do many objectifications. And another question is about algebra case theory. What Kubanev wanted to do is to categorify rings. So he wanted to find, he wanted to construct a triangulated category equipped with a monoidal structure so that the K naught of T is isomorphic to an interesting ring. But so in general, it's not easy to define a high algebra case theory for triangulated category, but if it has an enhancement by differential graded or homological context, we can define higher algebraic case theory. So they might have some interesting information for that. Okay, so, and Zora found a way to produce a Waldhausen category from a quotation pair. So we might be able to use his method. Okay, so I'd like to stop here.